In this lecture, we'll talk about a remarkable experiment that you can think of as a test for quantum mechanics. This is an experiment that was designed by John Bell back in 1965. So here's the history. We talked in the last lecture about this thought experiment by Einstein, Podolsky, and Rosen, and where they put forth this whole idea about local realism and local hidden variable theories. So what John Bell realized in 1965 is that there's an experiment which can distinguish between quantum mechanics and any local hidden variable theory. In fact, such an experiment was performed in 1982 by Alan Aspey, and it came out consistent with quantum mechanics and inconsistent with any local hidden variable theory. So this experiment has since been performed in many, many different forms to more and more greater and greater accuracy, and the experiments have always been consistent with quantum mechanics. Now, the actual experiments that have been performed have been used as simplification of Bell's theorem. This came about by Clauser, Horn, Shimony, and Holt. It's called the CHSH inequality, or the CHSH game, and that's what we'll talk about in this lecture. One thing that we should be very clear about with respect to entanglement, even though it seems at first sight as though you could use entanglement to instantaneously transmit messages from one party to another. So, going back to our example, suppose we had a qubit entangled with another one in a Bell state, and suppose this qubit, the first qubit, was sitting on Earth while this other one was put on a spaceship to Mars. You might imagine that when you measure this first qubit and you see 0 with probability half, and then instantaneously, if you see 0, the state of the new qubit also becomes 0. And so it seems as though you could have transmitted information from your qubit to Mars instantaneously. But if you look at this more closely, in fact, you can't transmit a message of your choice. What you get instead is you get a random bit here on Earth and the same random bit on Mars. The only question is whether this random bit was created before you actually transported the second qubit to Mars, or whether the random bit, the randomness happened at the instant when you measured it on Earth. There's a general theorem called the no signaling theorem, which says that you cannot use entanglement to send a message faster than the speed of light. Here, a message is a message of your choice rather than creating a random correlated random bit in different places. Now, what we'll see in this lecture is that even though you cannot send a message faster than the speed of light, you can use entanglement to create non-classical correlations. So you can create correlations between Earth and Mars, and these correlations would be instantaneous, but of a nature that you couldn't possibly create classically. And so to do this, we are going to have to explore the properties of entanglement a little bit further. Now we could ask a more general question. So instead of measuring this first qubit in the plus-minus basis, so here's 0, there's 1, there's the state plus, there's the state minus. Suppose I was to measure it in any arbitrary basis. So suppose I chose a basis like this. So this is the state u, and that's the state u perp. And let's say for now, for simplicity, we'll let u be a real vector. So it's of the form a0, 0 plus a1, 1, where a0 and a1 are real numbers, and a0 squared plus a1 squared equal to 1. Okay, so what do we expect? So if you measure in the u perp basis, what's the probability that you see the outcome u when you measure this first qubit? And if you make this measurement and it comes up u, what's now the probability that you measure u for the second qubit? Well, again, to answer this question, we should really write the Bell state in this u perp basis. And once again, we see something quite beautiful. So what you see is that, in fact, no matter which basis you write the Bell state in, it really looks like a Bell state again. So in the u perp basis, it looks like an equal superposition of UU and UPerp UPerp. Now this is quite remarkable. This is called the rotational invariance of this state. So let's try to work this out. Here was our picture, here was 0, 1, and we had some vector u and then UPerp. So if we call this A0 plus B1, then what's UPerp? Well, you see, if you look at it, this height was B, and so this would be B, but it's in the negative direction. So UPerp would be minus B0 plus A1. So now let's write out what this expression is. 1 over 2, this equal superposition of UU and UPerp UPerp is just 1 over square root 2 times what's UU? It's A0 plus B1 times A0 plus B1. And then UPerp, it's minus B0 plus A1 minus B0 plus A1. And expanding this out, we get A squared 0, 0 plus AB 0, 1 plus BA 1, 0 minus B squared 1, 1 plus B squared 0, 0 minus BA 0, 1 minus AB 1, 0 plus A squared 1, 1. Now remember, the state was normalized, so what we have is A squared plus B squared equal to 1. Okay, so now let's look at this expression. So you have AB 0, 1, BA 0, 1. These two cancel, BA 1, 0 minus AB 1, 0. And now what you get is 1 over square root 2 times A squared plus B squared 0, 0 plus, sorry, this was a plus, A squared plus B squared 1, 1. But remember, A squared plus B squared is 1, so you get back this Bell state. And so this is the rotational invariance of the Bell state. So let's see what this means. So first of all, what it says in a straightforward way is, if you measure this qubit in the UU-perp basis, the probability you see U is exactly 1/2. And then if you see U, what's the new state? Well, it's just UU, which means that now if you measure the second qubit, you'll see the probability you see U is exactly 1. You'll always see U. And similarly, if you see UPerp on the first one, you see UPerp on the second one. But now we can ask a different question. So suppose that I did this. Here's my picture, here's UPerp. So I measure my first qubit in the UPerp basis. But now what I do for the second qubit is I measure it in a different basis. So this was U, this was UPerp. But now I measure this second qubit in the VPerp basis and say there's an angle theta between these. So now I ask, suppose I measure the first qubit and I see the outcome U. What's the probability that I see the outcome V when I measure the second qubit, given that I saw U in the first one? Well, the answer is pretty clear, right? So, well, maybe think about, before you look at the answer that I'll go through, think about this for a couple of minutes and see if you can figure it out. Okay, so once you measure the first qubit and you get outcome U, we know that the new state is UU, which means that the state of the second qubit is U. Now what happens when we measure it in the VPerp basis? Well, the probability that we see the outcome V is exactly cosine squared theta. Let's look at the other case now. The probability you got UPerp was also 1/2. But in this case, if you saw the outcome UPerp, the new state was UPerp. And so if you saw UPerp, this was in the case that you saw U in the first qubit. If you saw UPerp in the first qubit, you could ask, what's now the probability that when you measure V, you see VPerp, this outcome? Well, this angle is also theta. And so by the same reasoning, this probability is also cosine squared theta. So the main takeaway message here is that if you measure the two qubits in different bases, the chance that you get corresponding outcomes u, v, u perp, v perp is exactly cosine square theta. The chance that you get differing opposite outcomes, is sine square theta. Now, so far we've assumed that u is a real vector. So u is a0 plus b1, where a and b are real numbers. Now, what if you wanted rotational invariance with respect to arbitrary bases? So say u was alpha 0 plus beta 1, for alpha beta being complex numbers. So now it turns out that you can look at this closely related state, which we saw actually in the last video. It was the state 1 over square root 2, 0, 1 minus 1 over square root 2, 1, 0. So this was the state of the spin state of the electrons in a covalent bond. This is the so-called singlet state. And if you use this state and you measure it in any basis at all, any basis u perp with arbitrary real coefficients, then it's rotationally invariant. So this is equal to 1 over square root 2 u perp minus 1 over square root 2 u perp u.